there's almost like a new force in the universe that selection drives complexification such to the point where systems can become self-governing, self-referencing. And when an object cares about its own existence in time, it's on the way to life.
Am I right in thinking that you're in Scotland now?
Yep, I'm in Glasgow.
Given the fact that we might be talking a lot about adaptation in this conversation, how have you adapted to understanding the accents of everybody that's around you in Glasgow? Did that take time?
I'm still struggling. I think the thing that I'm getting better at, though, is being water repellent.
Ah.
Because it's so rainy.
Yes. Well, as someone that's from the northeast of England, I feel your pain.
Yeah.
Yeah, it's a strange climate up there. What does life is the universe developing a memory mean?
I'm not sure I know now. It seemed like a good phrase at the time. No, I think it's the simplest way I can describe the process by soulless matter or stuff that's not directed is able literally to act on other stuff by experiencing stuff in stuff. Now, that sounds a bit weird, but I can unpack that because it's kind of interesting in that I think that I realized in the last few months that there is this transition to kind of from sand, if you like, all the way to cells, but actually via kind of functional objects. And if you think of sand on the beach, and the sand has no memory, so the wind is just blowing it around and, maybe water's coming in. But maybe every now and then some clumps of sand, maybe let some clumps of sand get blown together in a triangle and they become resistant to weathering from either side. And that triangle is able to kind of exist for time. And if that triangle can have a material effect on other sand next door, and that carries on, you can see maybe how the triangle could literally make lots of triangles. And so that, in a way, is like a little rudimentary memory because the effect of that chance arrangement has a material influence on the future. And so it's those little things that occur in the universe able to then remember that by physically building things, I think what I mean. As opposed to say, I don't know, if you've got a flame and you burn things, you lose. They're all the material that came before is destroyed and no longer exists. So it has harder time to have an influence on the future. And I suppose it's literally meaning that the past has an effect on the future because of the state of the past, like, what the shape of the object is. So that's really what I mean, is that the past really does have a meaning, which is obvious probably to us, but not to physicists who basically think the past doesn't exist.
I learned about slime molds a couple of weeks ago, and I'm aware that we're jumping ahead and we're getting into something that is definitely life, but they kind of have a memory thing, right? They leave hormones or they secrete pheromones and leave them around, and then when they go back, they can know not to go to this particular place. This is a mold.
Yep. And
they can train them to go through mazes and shit.
Yeah, exactly. I mean, slime molds are really good at doing that. Bacteria are able to communicate by that. So it's all this kind of, this idea, this constraints. Because the problem with life, the difference between life and non-life, when you've got life, like a slime mold or sand, right? Someone said, here's some sand, here's some slime mold. Can you tell the difference? Most people would be able to tell the difference. But that's that jump that you need to go through to get from sand to slime mold that people really had trouble with. And I think this understanding that the universe is kind of life is the process by which the universe not only has memories, but starts to initiate the process of recording those memories and making them more and more sophisticated so we're able to go to abstraction. So the going from sand to super intelligence is actually a fairly obvious thing that should happen in the universe, believe it or not.
What is the most difficult step, as far as you can see, from something which is completely not alive to something which is maybe as alive can be? Is it the origin of life? Is it going from single cell to multicellular organism? Is it not destroying yourself with global warming? Where along that spectrum can you see the biggest great filters?
Oh, I think I can think of three or four really interesting transitions. The way to put it. And so the first one is like, let's say the first transition is from the random to the kind of physical world where statistics rules and particles are everywhere to the kind of chemical world where things are a little bit less random because there's little bits of memory bonds. You can cut diamonds, they have faces and so on, so they have features. So you go so that distribution narrows slightly.
What would
So
be,
it's kind
sorry,
of
what would be an example of the first type?
just I suppose very basic particles, say hydrogen gas moving around, right? Gravity would tend to bring it together, so you clump together and you build a star, okay? But then when you go to, so you got this transition from in physics and chemistry to then biology. Biology, so let's say physics is just statistical mess, but Gaussian mess. Biology is also a mess, but biology is quite good at reproducing almost the same features. So if you had a twin or you had some identical cells, they'd be different, but you could see that they were the same thing, or a couple of cats. So, but they wouldn't be like just random mess. There'd be a narrower distribution. You identify the cats. And then if you go from cats to the iPhone, several iPhones, and you look inside the iPhones would be pretty much identical. Same PCB, same kind of transistors if they're the same type. So the distribution would narrow almost to a thin line. So you have broad distribution, kind of random one, narrower one for biology, and a thin line for technology. So what is really interesting is that transition from kind of a random distribution to a less random distribution for biology, which is evidence of evolution, and then evolution to technology. So you're saying, what is the hardest jump? Well, I think the hardest jump is basically because we don't yet understand the force, if you like, that able to initiate evolution. Everyone thinks that evolution is something that only exists in life. But if that's the case, where did the life come from? And you have this proverbial, I think it's not impossible to understand how you go from a single cell to multi-cell. Hard, but not impossible. Not impossible then to go from multi-cell to animal, and then animal tool making to consciousness and stuff. But so that first jump from the sand to the cell, the molecular machines, is something we have no handle on because it occurs in the molecular regime. And so this is where the chemists need to be doing their detective work. So I think that we should nail it soon, but it is fascinating that we have no idea what happened. None.
That's the current state of the origin of life research, is that we have no idea how it happened.
I mean, I think I have an idea, but that's because I'm biased. I'm doing experiments. I have an inkling. I feel like I'm the first to a party, like the electricians, when people were inventing electricity. You had all these arguments between the voltas and the amperes, and some people thought electricity was a liquid. Some people thought it was, they didn't really know because there was static electricity, so people's hair standing on end. There were batteries, and there was this paradigm where no one knew. It was a free for all. So, and no one was completely right and no one was completely wrong. There's a spectrum. And I think right now we have what we call prebiotic chemists who basically go back and just try and recreate the events. We have biologists who say, chemistry is easy. Well, let's get to genes and go from there. And then you have people who are trying to understand the origin story to say, well, we need to kind of let go of life on Earth as being the only thing and say what general process gave rise to life. And I'm probably the first in a new discipline of people that are willing to say that this is an answerable question. And in fact, I have experiments running in my lab right now, literally just shaking sand in a box, hoping for slime mold to come out, or maybe something a little bit less scary than slime mold, right?
You're shaking sand in a box to just see what happens.
Literally, I mean, it's a bit more chemically sophisticated, so it probably would have some water, and in that water we'd have some inorganic minerals, some rocks, and those rocks kind of act like, the beginnings of, if you can etch a rock and have a little cave in it or a chance crack, that crack becomes a place where a memory can be born, because that crack maybe can trap some molecules. And those molecules will be given safe harbor from the environment. So those molecules can basically react with each other to make another molecule. And if these come together, you'll keep building more and more possibilities to explore chemical space. And then in chemical space, there are some special molecules called replicators, which only occur very rarely, but those molecules are able literally to fabricate each other, or even better, fabricate each other in groups. So it's almost like imagining having if you have someone fabricating a table and a chair, like a carpenter, you imagine that the table fabricates part of the chair and chair fabricates part of the table, and together the table chair exists as an entity. And that's how the thing evolves, because it doesn't need the carpenter. It's a symbiotic relationship. And that's the thing that we're searching for in the sand shaker in my lab.
Why would it be sand with water, given the fact that life is carbon-based?
Yeah, good point. So because carbon's just a useful. It's a useful element because it can make a large number of strong interactions. So the reason why, if you take plastic and flex it and bend it and so on, that's all based on carbon. And carbon has that property to make what we call polymers, and those polymers are really versatile. And so on planet Earth, the carbon was in the form of methane and probably carbon dioxide, the simplest forms of carbon. And then what happened? There was a load of, there's obviously hot rock coming out from the center of the Earth, and there was water probably, and the methane would probably start to form tar. Reactive oxygen formed tar, sugars, not living sugars, just really, really terrible, gooey black tar. The CO2 would also react. So these polymerization reactions would happen, but they would happen in the sand, and the sand would act as like a catalyst or a controller to basically, direct the outcome of those reactions. So literally my lab is like a load of methane and carbon dioxide in a load of sand being heated up. It's a kind of messy pile of junk.
And is there a machine, a little automated machine sifter that's just wiggling boxes?
We can do shaking, but we do stirring. We have networks, and we have like basically it looks like a load of different test tubes. So maybe say a rack of test tubes or two racks, but they wouldn't be isolated. They'd be connected like a network. So we kind of make the chemical internet. So what we could do is we could transfer the contents of one test tube to another to seed all the different test tubes. So we literally really spread all the material around for maximum searching of the chemical space.
So how do you define life? What's the difference between life and not life?
Physically, no idea. Because in fact, I would say, I'm being facetious in a way, but I think it's really important. I think that I will now contradict that and say, of course, this is a definition of life. In matter, if you let's say if I take a snapshot of you frozen in time, you would be as dead as a rock, right? I'd see, and I take the same snapshot, I would not be able to know you're alive. So it's not just the stuff in you, right? If you shed a tear, the water came from a living eye, but the water doesn't have any emotion. It's just water, maybe some salt in it or something. So people get really stuck thinking that life, they have to kind of say life has these properties of, you've got a metabolism, you've got all this stuff and whatever. And I think that's far too hard, because you end up having to take a survey, a focus group. Hello, alien, can you please tick these following questions? If you say yes to most of them, you'll be alive. Do you respire? Yes. Do you evolve? Do you metabolize? Yeah. And NASA got its stuff. It's kind of got really stuck, because if you say to COVID-19, is COVID-19 alive? It's a virus particle. Most people will say no, viruses are dead. Like, well, okay, good, no problem, no pandemic. Well, of course, that's incorrect. When a virus particle gets into your cell, it hijacks the cell, gets its nuclear material replicated, makes lots of copies of itself, leaves the cell, goes around and can carry, that's its life cycle. So a friend of mine who kind of was the last person to touch the Hubble, is an astronaut. I tried to convince him of this about life, difference in life. So I said there's no difference between him, the astronaut, and a virus particle. Except when he's in space, he's like a virus particle. He can't have children. when when his oxygen runs out and everything runs out, he's going to be a dead astronaut. He has to come back to Earth, and on Earth, he's able to breathe, have kids, or look after his kids, whatever, do stuff. So the current notion of life that we have is not appropriate. So now I ask a different question to, is something to life? Is to say, okay, let me, take you or an object, and you say, right, is this a product of a living system? And then, or evolution. And I have a way of giving you an answer to that question with almost 100% accuracy. And so what I define life is a process that can build objects that cannot form in a random environment. So I'll say that again. Life is characterized by the ability to build stuff in abundance that can't form by random chance. So you can think about DNA and proteins and cells, but you could also think about this mouse. This mouse, if we go to PC World and buy 10 of these mice, it's a Microsoft mouse, it's probably okay. If you found 10 of these mice on Mars, you wouldn't say, oh my God, it's a random rock. You'd be like, that's weird. There's 10 electronic things that look like a mouse I found back on Earth. They're identical. This must be proof that life has been here. It might have dumped the mice off and ran away. But those objects, they don't need to be alive themselves, but they are a readout on life. So I think, don't ask if you're alive, ask if you can leave artifacts that prove to other people who follow your trail that you were alive. When you do that, that's so liberating, because then you see flame isn't alive, the spot on Jupiter's not alive, clouds aren't alive. But if you found, 10 identical clouds in the sky with lots of features, you would know they weren't clouds. That was evidence of life in the atmosphere.
So you're not saying that the mouse is alive. What you're saying is that something which seems to present a highly ordered environment that couldn't come together by chance is either life or an artifact that shows that life was there.
Exactly.
So
that's it.
This is intrinsically related to time and entropy in that case.
Yes.
How?
Yes,
How?
yes.
Why?
Well, you might know that I'm not really a lover of entropy, or you can choose one or the other, right? You can choose entropy or choose time. And so what I mean by that is that because we live in a universe of physicists think that time does not exist, we have to have this thing called entropy. And so what that means is that in the universe's entropy is expanding, which is another way of saying the universe is asymmetric and there's time. So entropy is just this. It's kind of a nonsense. It's actually a kind of nonsense term. I feel bad for Boltzmann because I'm a chemist. I love setting fire to stuff, right? And I'm not saying that the second law of thermodynamics is a falsehood. I'm saying that the second law of thermodynamics is a misrepresentation of how the universe works. So lots of people think the universe is going to end a heat death. I don't think that's necessarily guaranteed.
Why?
Because I think the universe is going to basically end up just keep building stuff. I think there's a series of ratchets, and humanity's been doing it, technology ratchets. And what happens is that basically we take all the available energy and resource, and by abstraction we build machines that can then harness more energy and resource, more sophistication. We go up and up and up and up and up and up and up. And I don't think that needs to be a heat death. We can regather those. Now, that means that actually there's something very interesting about what we mean by spontaneous processes in entropy over time. But I'm not saying that time doesn't exist. Time must exist. And because time exists, the universe expands. And because the universe expands, there's more space over which you spread stuff out, which is what the second law in entropy says. But that doesn't necessarily say that everything has to spread out and die, right? There needs to be enough resource to get there. But we just don't know enough about it. And I like to poke the physicists. But I don't want to go too far because entropy is a useful measure of labeling. Or if you look at if I give you some snapshot of a room, let's say my office here, and I put some neon gas in my room, or no, let's say some radon gas. So I wouldn't want to be here because it'd be radioactive. But I had some goggles and I could see the radioactivity. And I put in a plume of radon gas in one corner of the room. It'd look like Ghostbusters. You have green plume, right? So what would happen? That would be at t equals 0, what would you predict would happen at t equals 1 hour? Well, then the radon gas would spread out uniformly in the room, and you'd kind of have this green haze. So you would basically, when I give you those two photographs, which is the beginning and which is the end, you would look at it and go, oh, that's the beginning and the end. You would assign that. You would label it. And so the funny thing about that is that you have to be the labeler, but you could somehow take all those molecules, and if you flipped all those molecules back, you could push them back into the corner. You would do work on them, and that work would be against the second law. It would take some energy, and that's all kind of accounted for. So I'm not saying there are perpetual motion machines, but I'm saying that probably the energy of the universe is not constant. The energy of the universe is increasing, and that energy of the universe increasing is because of time, and that's what dark energy is. The mismatch in dark energy in the universe is not dark energy, it's just evidence of time, I think.
Go into that for me.
So there are two things in the universe we don't understand. There's dark matter. What that means, if you look at all the galaxies right now and you calculate you look at the size of the galaxy and the rotation and the fact there's a compact mass, if you do calculations with gravity, you do calculations of that observable mass, and you look at the structure of the galaxy should not be holding together, it should be flying apart. So some of the mass is missing. So the physicists said, well, we can't see it, let's just call it dark matter, and there's stuff in there. I think that's okay. That could be a hint there's something wrong with gravity, but I think most physicists are fairly comfortable with the fact that there's some non-luminescent stuff that's in the galaxy called dark matter. Gravity attracts together, galaxy is lovely, fine. So that's dark matter. Let's not worry about that. But there's this other thing called dark energy that we need to somehow understand the rate of expansion of the universe and to balance things out. And we just don't know what that is or where it comes from. And my wild idea is that the amount of dark energy in the universe was 0 at t equals 0 because there was no time. And as the universe increases, the energy expands in time. The energy of the universe increases because of the energy associated with space. And because time came first and produced space, the energy associated with space is just inflating. So it's almost like the singularity at the beginning is pulling energy from non-space, which seems really weird, but that is really weird, and inflating into space. And we're actually measuring that. Evidence of that is dark energy.
How do the physicists feel about this idea?
They just don't talk to me about that. They just ignore it. I think because they are, for some reason, time is an emerge. They have to, well, what they feel about it, they just think I'm talking complete nonsense, truth be told. Some physicists who think that actually not entirely. Let's be fair. They are confused because I'm unable to give a precisely defendable theory around that. But what I say is like, well, for the universe to have an origin, what we have right now, the universe must have had lots of order at the beginning. Everyone agrees this entropy that we got, this order at the beginning is allowing us to run down the clock of the universe. So if the physicists are right and entropy is expanding, increasing with the universe, that something put that order there at the beginning. And that means the initial conditions of the universe were set. That means what happens to the universe actually is pre-controlled by the initial conditions. That all the questions you're going to ask me today were not decided by you in the last few hours or by you doing some research, but by the universe at the beginning. So, the first photon that came into existence and then underbroke symmetry breaking, so that all happened. That's clearly nonsense. And the reason why that's clearly nonsense is there wasn't the information capability in the universe there. So that means there's something wrong when you're saying the initial conditions prescribe all the future, because they could barely prescribe the next moment. So actually, the physicists are in a trap in that the origin of the universe requires order. And if you give that, then you can get rise to the second law, time is emergent, causation is emergent. But you have to get this order from somewhere. And then you have to make these 4 beliefs. So order at the beginning, time is emergent, causation is emergent, second law. If I just say there's time and it's asymmetric, you don't need those 4 beliefs. because the second law is obvious. You don't need it. You don't need order to be in the past because there's just time going forward. There's always going to be more disorder or a larger space from which to spread out your matter in the future. So all that breaks down, but that requires the physicist has to give up the initial conditions, and that's really hard.
I can't imagine why they don't want to play with you, given the fact that you're curling one out in the middle of their lovely, very well-established set of rules and procedures that everything's been based upon.
Well, I mean, I do think that the standard model and the Newtonian dynamics we've got and the Einsteinian dynamics are pretty damn good. Pretty damn good. Planes, trains, automobiles, going to the moon, making transistors. So physicists have got strong, it works. However, it doesn't predict life and novelty and creativity. And the fact that we realize there's something wrong with our universe is the fact that human beings are able to be creative and almost think beyond the edge of the universe. When you have a creative thought, that thought is almost existing beyond the edge of the known. And then you can take that thought and actualize it in the known universe. It's kind of insane.
You're going to come up against physical, real restrictions. You can think things that you can't do.
Sure, but you can also think things that you can then have a material impact in the universe, that unless you thought of them, they wouldn't have happened. So SpaceX, Elon Musk deciding to land a rocket on legs, someone invented that in their head, and now rockets land on legs.
I have in my Twitter bio locally reversing entropy as a little tagline. It's been there for ages. I heard it in a podcast years ago, and that it kind of is one of those. Is that an accurate statement to say that human beings and life does locally reverse entropy?
Yes, I think it's more than that. I think what that is a marker. That's a very nice way of saying gently that the causation and memory in the universe is a thing. And what you're able to do by let's think about the thought experiment. So what you can do when people think about reversibility, and you say, right, we're going to do an experiment. Let's imagine a universe without time. But hang on, you have to stop. It requires time to do that. It's kind of insane that to imagine a time where there is no time, you have to stop and time goes by. It's kind of insane. And it's almost like saying, right, let's imagine a universe in which all the prime numbers are available. Okay, tell me all the prime numbers are available, but you don't need that. You need a resource called time to actually mine the prime numbers. So the existence of ever-increasing prime numbers is evidence that time exists. The fact that I can't steal money from your bank account, well, not that I would try, but let's say I would just, by breaking your encryption key, is evidence that time exists. So, because physicists will all be rich otherwise. So this locally reversing entropy is a bit about saying, well, we need to do work on our environment. By doing work, we can position objects where we want them to be, which fights disorder. We set the initial conditions, we can make objects and so on. And that's kind of the way that I started to build assembly theory, which is from controlling those initial conditions and causation. And I just think that, I think that entropy hasn't really done very much for us. It should have done more.
I like that idea. Okay, so going back to what you touched on earlier on about the origins of life, you have an inkling. You're the first guy at the party. Is it tar and primitive sugars, or what's going on? What do you think?
So going to the origin of life, I think that's a really important question. I think it goes beyond that. What I'm trying to do in my lab, not just in my lab, but collaborators in the US and Germany and all around the world. So lots of people coming to the party at the same time. But there's a physicist I'm working with at ASU we're kind of on the same page there. And what we think is happening is that selection, the process of selection, making memories, can occur before biology and life. And selection occurs in stuff. Where there's just any physical stuff, selection can start. And so what that allows us to understand is that selection in matter predates biology by a long way, and that starts to weave those memories. And over time, molecular machines get built, and those molecular machines are recruited by the available chemistry you have on Earth. So the origin of life is about inventing selection, I think. And selection comes before biology. And that's what our inkling is. And so on Earth, that leads to carbon-based life. But I think elsewhere, there's going to be loads of other possibilities. So I think that we want to understand how selection predates evolution. And I think that we've come up with, we understand there's almost like a new force in the universe, that selection drives complexification such to the point where systems can be, I don't like this phrase, but I'll use it anyway, become self-governing, self-referencing. And when an object cares about its own existence in time, it's on the way to life. Because you have a number of ways existing. If you're a rock, you just sit there and do nothing, and you're made of hard stuff. But if you're sand, you'll get blown away and broken up all the time. And the fact that we exist, the meaning of life is like existence, literally just one word. Existence through adversity. Because there's weathering and so on, selection allows you to build repair mechanisms. So what we're doing in the lab is we're building experiments from the inorganic world that go and undergo selection. In this case, they work with organic molecules, and they start to produce molecules that will turn into a kind of biology. But I'm pretty sure the biology we have on Earth, the life we have on Earth, is unique to Earth. There is no other biology in the entire universe. And what I mean by biology, I mean proteins and DNA and the specific nature of the stuff. But life is everywhere. And I think that life is likely to be as common as, stars. And
hang on. So life on Earth is completely unique, but life in the universe is widespread.
Yes.
So your view, it seems, is we have a very myopic understanding of what life consists of, because we're only looking at carbon-based, this particular atmosphere has to respirate, has to do the sex thing to make more of itself and replicate and stuff like that. And your view is much broader than that there are essentially as many ways to create life as there are potentially planets to have life on.
Yeah, and I think there will be commonalities like in stars. I'd like, if you take our star at the center of our solar system, if we just pretended we couldn't see any other stars in the sky, there was just one star, we would probably look up in the sky and look at this star and obsess about how did it form, what were the conditions that made it, and all that stuff, and obsess. Now the shroud has been taken, and we can classify stars everywhere, by the luminosity and the size and so on, and their spectrum, that we know that basically there's a whole statistical distribution of stars, and which our sun is one of those. And I wonder if we could, I don't know if we ever will be able to survey life in the universe that will see life like that. And then it's kind of cool to think about that, because what I would like to do is convince NASA and ESA, say, well, look, with telescopes like JWST, we should try and survey stars and planets, and try and look for planets that may be of a rocky planet, similar conditions, similar mass. Why? Because we know that life like us, that works on the second to hour to day time scale, exists there. And that's why we might be our best chance of identifying aliens, because probably life can exist anywhere. But is the timescale right for us to talk to? Is the chemistry right for us to recognize? There's so many variables, so contingent, that it's going to be really hard to understand.
What are some of the commonalities that you're going to see between all life? Between most life, should I say? I
would guess, and this is just guess because we've just got life on Earth, that evolution will be common, because selection and evolution go together. So you'll have an entire ecosystem where there'll be lots of different life forms sharing common machinery. So that'd be one thing. I would think that probably the ability to have some kind of not computing device, some kind of information processing device, some sensors, maybe depending on the mass of the planet. Imagine if life started on a planet where the gravity was less strong. We might not have needed to wait so long to get to multicellular life form, because one of the reasons why it took so long is we needed to develop oxygen metabolism. Oxygen metabolism took ages to develop.
Why did we need that? Because of gravity?
Yeah, because of gravity was strong. Oxygen gives you more energy, just really super boost.
You're just fighting against Earth.
Yeah, so if gravitational strength was less, maybe Earth is at the bottom of the class in IQ because it took so long to get intelligent.
And on a planet that didn't have as much gravity, the organisms would be able to grow more quickly, which means that they would be able to become more sophisticated more quickly, and they'd be able to develop and become a
Yeah.
type 3 civilization. Okay, that's interesting. What about other exotic forms of life? So I watch a channel called Melody Sheep. I'm not sure if you've ever heard of it. Dude, you would adore this YouTube channel. So these guys make documentaries on YouTube, about one every year to year and a half. And they're usually between 30 and 60 minutes long. The whole thing's beautifully soundscaped and rendered in 3D. It's unbelievable. It looks like it should be on Netflix. And they've done, I think, a 3-part or a 4-part series, which is looking at different ways that life could have evolved on other planets. What would have happened if it was very high gravity? What would have happened if the atmosphere was unbelievably more dense? And you can have these creatures that are kind of like whales, but they surf through the air. And then they moved on to some what they called very exotic types of alien life. And one of the ones that they mentioned, which is why I brought it up with the sand earlier on, is silicon-based life. And they said that if you had silicon-based life, metabolisms could be so slow that thoughts might take millions of years. And this is my only tangential bit of consumption, apart from your work that I've had into this world. So can we have silicon life? What other exotic types of life are there? And can thoughts take a million years?
Wow, I think a thought can take as long as it needs, as long as the environment doesn't change such that you break registry. So millions of years, I don't know. I'm going to watch this YouTube channel. Thanks for the tip.
I think you'll absolutely love it, man. It's so good.
I think that you thoughts could take, let's say, days, because I think silicon might be faster because silicon can move electrons around. We might have diamond brain. There might be aliens with diamond brains, right? So or graphene brains. So because of what you can have is you can have highly ordered carbon and have these networks. And if you dope the networks, it might be such that you can just basically say, here's a big diamond. We'll use that as an information storage medium. And wherever we break, we have dangling bonds and diamonds or defects. That can be, I'm just making stuff up. So the problem that we have imagining silicon life is that silicon requires high pressure, high temperature, all this stuff to happen. But I don't know what the lifespan would be. If you're talking about millions of years, we could do the math. Humanity's been around for a few 100,000 years thinking. And so and the universe has been here for about 13.7 billion years. So it's, 1,370 million years. So probably not, because we won't have had many thoughts since the beginning of the universe.
Yes, I understand. Okay, what other exotic forms of life have you considered that there might be out there?
Oh, I think silicon's a good one. I think on Venus we might have complex chemistry getting to there. I think that there might be different forms of life on Titan and Europa based on carbon, but completely different weird stuff because it's liquid alkanes, very cold. So the type of chemistry you got available is not going to be as rich as you have on Earth because you won't have the set of compounds. But really, the periodic table is pretty big. But what I think you're going to see is that when stars form, we know that stars go through a fairly normal kind of life cycle. So they undergo fission, they keep building up elements and complexity, so more and more heavier, and then the star explodes, then that material accretes, and then what happens is the heavier stuff goes to the center and you get fractionation. So I think that most rocky planets will present with, iron and nickel core, lighter elements on the outside. So I think exotic life will be very kind of exotic, but not completely outrageous. I don't know if you know the book by Andy Weir, the Hail Mary.
Yes, yeah, where he has that creature. What's it made of? What's it made of?
So it's made of mercury blood, but by kind of biological, but kind of inorganic and hot temperatures. Kind of cool. I like the research gone into that. So I'm not sure I could buy that a life form would have a mercury blood because that's really heavy and really you'd have to have a lot of mercury. But it is a readily available liquid, right, under a large variety of conditions. But I think, to be honest with you, we simply don't know. And I'm a chemist existing on planet Earth, 1 atmosphere, 25 degrees Celsius, liquid water. Imagine what a chemist on Jupiter would look like under several million pascals of pressure, where hydrogen is not only a liquid, it becomes a metal and it conducts electrons, right? So it's like super interesting. So I would just say, no, I wouldn't have a bet against anything, but I would bet that you would need to be able to measure the complexity of the object using the kind of the way I discussed earlier, looking for artifacts and examples of non-statistically formed objects that you could discern from the background.
Given the fact that you think there's going to be life not only out there in the universe, but in planets that are next door to us within our own solar system, are you concerned that this has implications for the Great Filter hypothesis, Robin Hanson's thing, where he says that it's an answer to the Fermi paradox? There's something big that all civilizations need to get past. If we find life elsewhere, this means that we've got some huge filter to come up against.
No. I think there's another big filter. You know what the big filter is? Expanding space and the speed of light.
Oh, that you can get captured in some corner of...
Well, it's hard to get from place to place. I mean, okay, what's more likely? That we're moving faster from away from each other to approaching the speed of light, or that we've all... I think the human life on Earth is in danger in the end, but life on Earth is going to do just fine.
Ooh, I mean, why that? Why human life's in danger?
Because wait until Skynet comes. It's going to have much more fun. It'll be resilient to the expanding sun, you know.
You think we're going to get AGI'd out of existence?
No, I think we won't. I mean, I'm being really flippant, but we're already become cyber-physical right now. You know, I have my phone and connected with that, and then we'll have more and more kind of interactions with technology. And so, and I'm very hopeful about the future of life on Earth, that it won't, obviously humans are going to transition, but the race we're in right now, well, we're in a race to not be idiots, right? We're in a race to educate each other and give everyone a degree of equity with the population, and we're trying to get out of this view that there are limited resources, and we need to basically kind of have certain people constrained because of those resources. Once we understand we're no longer resource constrained because of technology, the humanity is going to have a field day. It's going to be so fascinating watching it the latter half of the century. We need to kind of sort out climate change, and sure, it's dangerous, and sure, crops could fail and water. But you know what would happen if crops fail and water scarce? A load of people die. Tragedy, sure. I don't want to die, but not everyone will die. And then humanity will go again. So, you know, I don't think there's a great filter. I think that maybe there's a great filter on his imagination.
Oh, dear me, Robin Hanson. I understand your idea around the fact that, and this is similar, I'm going to guess, to the ratcheting thing that you said from earlier on. I understand your idea that technology opens up capabilities that you can't see. It's like the unknown unknowns of progression that you can move through. I also think, yes, a lot of the problems that we're coming up against that look like X risks from the outside are probably not true existential risks, as in 100% of all humans are extinguished, or that we are irreversibly put into a situation that we can't get back from, whatever it is, irreversible civilizational collapse, two versions of X risk. I think you're right. There's some, maybe, you know, the bioengineered weapons, not tremendously fantastic, pretty fucking robust, probably going to do a good bit of damage. But even nuclear war, you know, you set off all of the nukes on the planet, it doesn't kill everybody. It's not nice, and it wouldn't be fun for quite a while, but it doesn't kill everybody. So yeah, you're right. Humans are very, very resilient. And then so would you class yourself as a techno-optimist? I don't even know what that really means, but I hear people say it on the internet, and I feel like I should use it.
I think that I'm trying to get command of all matter, right? I'm trying to create origin of life. I'm
you
building
sound like
robots.
Thanos.
No, because Thanos. No.
Command of all matter.
But I mean, I'm trying to literally program matter digitally. So I want to get digital control of matter to basically build stuff, and I just need information and energy for that. So there's enough energy coming from the sun for me to transform all the matter on Earth over time. In fact, biology's been doing it, arguably. So I am an optimist, and I think that we should enable people to have a growth mindset we've got political difficulties and so on. There's all sorts of interesting things like humanity's coming. We're understanding what economics is. We're understanding what creativity is. We're understanding that we are pretty interesting in a causal chain, that we're worth preserving. And I think that this kind of, we're also understanding that our culture communicates some very deep and important truths about our past into the future that we don't know yet how to write down. We are recording some of it, and we're capturing, even if it's like in the manifestation of YouTube and TikTok. So yeah, I would say I'm a techno optimist, not just because I'm living in some bubble somewhere, because I can see as a chemist, what has chemists done the last 50 years? We've stopped the population from starving. We've decreased infant mortality. We have basically cleaned up the environment. Yes, and we need to do it again. And oh dear, we have to remove the plastic. And oh dear, we have to remove the CO2. But we'll do it again, and we'll keep doing that. And I think the great filter, perhaps the really great filter, is climate change when the sun expands and engulfs the Earth. But even then, we might have like pushed the Earth back a bit or evolved into,
I was learning, Anders Sandberg is working on a book at the moment where he's thinking about, what's he call it? Galactic landscaping. Where precisely that. I've got this lovely view, but there's this planet in the way, and if I could just get that, oh, lovely, or whatever it might be, like moving an Earth or a habitable planet away from a sun that's about to expand and destroy it, or whatever it might be. Yeah, I do think moving forward that you're going to see far more opportunities open up. I would say that technology provides us with a lot of unknown unknowns. That means the potential in future is going to be really, really hard for us to grasp.
Mm-hmm.
What about the chance of any life in space? Is that completely beyond the pale, that something might not need a planet to exist? Maybe it could have come from a planet and now either exists in space, or it could be born in space. Is that a thing?
I don't know. I mean, my guess would be that it'd probably find getting a date hard, because space is quite big and gravity is quite useful to locate you, and also. Being in a solar system is useful because you've got access to a reliable energy source, because you're typically going to be orbiting a star. There obviously is a chance that perhaps a civilization gets propelled into space, maybe their planet gets ejected. Is there an example in the universe where a planet was happily doing its stuff and a good civilization has emerged, and suddenly the planet got ejected from the solar system and they had to quickly adapt? And they had enough resources to carry on for a while, and it almost became like a lifeboat, and they're trying to work out how to get captured by another solar system. That could happen. That might be pretty grim, actually. So just imagine getting thrown out of your house. If you get thrown out of your solar system for bad behavior.
That sucks. You don't want to be there.
So I don't know. I mean, I think the gravity is useful and energy is useful. And our solar system has been quite a nice little house, backyard for a while. We've got the asteroid belt. We've got Mars nearby, Venus nearby. We've got obviously the planets on the outer solar system, which were the garbage collectors at the beginning and now stabilized. And we've got this pretty pleasant sun. And so, I kind of like where we are, but I'm biased, right? I guess we all are.
You're designed to like where we are.
Exactly. I'm evolved to like it.
Yeah. Why do you think that chemistry doesn't seem to have captured the public's conscience or a consciousness in the same way as something like physics has? When I see a chemistry documentary, I go, oh, look at that. That's a chemistry documentary. And then there's swaths and swaths and swaths of stuff about space and physics and even biology, right?
So I think because chemistry is hard in the middle. So physics is so wondersome because it's so simple, right? And it's not that simple, but physics is a low memory affair. So there's not many rules you need to basically create the stuff. Then when you get to chemistry, you have the periodic table and all this information and stuff going. So it's quite piggledy. But then when you get to biology, although it's messy, you now have cells, you have variation, and you can see the genome. So I think that chemistry is kind of trapped between the simplicity of physics and the just splendor of biology, and we're too busy, curing cancer and
getting the work done.
Getting the work, yeah, I should say that. Yeah.
Bloody hell, shots fired. Okay, so talk to me about. You mentioned earlier on viruses, and you made an analogy between a human not being on Earth versus a virus being basically outside of what I'm guessing would be a host. Mm-hmm. Have you considered whether, is it likely that stuff like that would also be on other planets, other types of life? Would it be typical to see parasites and viruses and other things like that?
I think so. I mean, and I also think that perhaps the origin of life was a virus origin of life, and that things really get together in the dance for so long, and that would maximize the ability to explore the solutions. And then cells were a relatively late comer to the machinery, and the cells were just like kept stuff together. It's like, right, I'll have you, stay together, please, replicate together, rather than chance happenings. And I think there is reason to believe that selection will occur at that kind of level over the universe. And I would wonder if viruses are a universal characteristic of life. But wouldn't it be fascinating if we go to Titan, or indeed we find viruses coming from the outer solar system that have completely different technology or evolved technology, that we can see it's complicated, we can see it's biological-ish, but we don't recognize the base pairs in the DNA, and we don't recognize the protein. That would be mind-blowing.
I read a blog post a while ago talking about how it was a potential answer to the Fermi paradox, talking about how a lot of life may evolve underwater. There's a lot of water out there, liquid water. One of the problems you have with liquid water is that becoming an advanced civilization is pretty difficult because you can't smelt shit. You're not smelting anything, and you're not flying anywhere on an ice ship. Is that something else that you've considered about the way that life that's exclusively underwater could perhaps develop?
Probably. I mean, it might not have any version, but I think the Fermi paradox is not a paradox. It's just because Fermi's imagination wasn't big enough. And I just think the problem, but so everyone is coming up with reasons why that stuff doesn't happen on the data point of 1. I know, so I'm pretty sure there's life everywhere in the universe, but it's a continuum. So you start from almost non-life, sand. You go up, selection, kind of some autonomy at the cellular level, multicellularity, animals, intelligence, rockets. And I think that we are basically characterizing it all wrong. We shouldn't be looking for an on-off switch. We'd be saying, oh, there's more memory there than not. So there's probably the process that gives life everywhere, but can we go and talk to someone? Well, and I think the reason Fermi didn't understand is that the causal chain of events, the fact that we can talk to each other and everyone on planet Earth can kind of understand the culture, is that we shared a common ancestor, and that, from mathematics to singing to whatever, we find an alien, we might not actually know it's an alien. We might not even understand we're seeing it. The Fermi paradox might just be basically a polarizing filter on your eyes, and you just can't see the evidence of life, which is why we have to build a new detection system to look for complexity first, and then put it on a scale. And that's one of the things that I'm doing, because then I can build a machine to make complexity and say, how complex is it, and how much did I cheat? Because I'm cheating in my lab, right? Everyone says, my joke is like, I'm not a creationist. I'm not a creationist, but I want to be one. Which is basically, I don't believe in a creationist God, but if I make the Croninites, they are going to worship me. I'm going to make sure of it. Fantastic.
I love it. Look, Lee Cronin, ladies and gentlemen. Lee, if people want to keep up to date with the work that you're doing and your lab and all that stuff, where should they go?
So my Twitter, at Lee Cronin. Also my webpage, croninlab.com. And just use that Google thing.
Lee, I appreciate you. Thanks, mate. What's happening, people? Thank you very much for tuning in. If you enjoyed that episode, then press here for a selection of the best clips from the podcast over the last few weeks. And don't forget to subscribe. Peace.